These are notes about strong and weak acids and bases, and also we're going to start talking about something called Ka. So yesterday, you guys, we looked at, we started to talk about strength and in terms of ionization and conductivity. So a strong acid like hydrochloric acid is going to be a really good conductor because it breaks into ions so much. Whereas a weak acid like acetic acid is going to break up to some extent, otherwise it wouldn't be an acid, but not so much. So the conductivity was less. So just a little review, so a strong acid like HCl, what's happening in water is it's completely ionizing. There's really no intact HCl anymore. It's just the ions. Whereas we also have strong bases. This is something we're not going to focus on quite as much, but just realize that there are strong and weak bases too. So a strong base is going to break apart 100% also into its ions. So let me show you what I mean. So if you were going to write the dissociation for sodium hydroxide, it would just completely break up. So notice we don't even put a reverse arrow there, because it's not really going to stay intact if it's strong. We also know that we have weak acids. So here is carbonic acid. You can see the green is the intact acid that stays together. And then if it were to dissociate, so now I'm going to put the double arrow because most of it will stay this way. If a hydrogen ion comes off and does break up to some extent, this is what you get. So you can see that most of it's together, just a little bit of it broke apart. So we also have weak bases. So I'm not going to necessarily show you the reaction, but just know that they mostly stay intact and then they don't break apart or give up their hydroxide ions. Or in the case of ammonia, you would have to look at that as a Bronsted-Lowry base, and most of it stays intact and doesn't accept a proton to become ammonium, the NH4 ion. So a generic way of writing an acid is HA, and the A is just any anion. It could be just a single element, chloride or fluoride. It also could be a poly. So when I write, I can dissociate that into H and A, and then in the speaker, if it's a strong acid, I would have all of those just broke apart. And if it had been weak, I would have kept a lot of those together like this. Let's say I have the beaker here, and then maybe one of them is broken apart. Another thing when you look at the dissociation of a strong acid is we can show it kind of with a bar graph, and this is the number of moles of hydronium, or same thing as hydrogen. So sometimes you'll see that we write it with water included, and then you can see if you look at Bronsted-Lowry, this is the Bronsted-Lowry acid. Water is acting as a Bronsted-Lowry base. This would be the conjugate acid, and this would be the conjugate base. So to simplify things, a lot of times we're just going to take the water out and think of it just as the acid giving us the hydrogen ions, which would then attach to water and form hydronium, but we can just leave it like this. It's a little bit simpler to see, but if you like the other way, that's fine too. So strong acid, equilibrium lies to the right, because we're going to just have this and really none of this. And then the conjugate base is weak. So what does that mean? So our conjugate base right here is weak because it's not likely to go back and reform the acid, because this is equilibrium lies to the right. This is not likely to accept a proton and go back. So we can also look at this for a weak acid. So a weak acid, after it dissociates, you're going to have mostly the intact acid. So the equilibrium would lie to the left. I'd mostly have this present. And then if I were to, this is my Bronsted-Lowry acid, and then it would be tied to, this would be my Bronsted-Lowry conjugate. I guess I don't need to use all of that, but it would be the conjugate base. So now this base is strong because it's likely to accept a proton and go back and form HA, because mostly what we're going to have is HA intact. So the equilibrium lies to the left. So I want to talk about Ka expression. So if I do have this generic reaction for an acid, whether it's strong or weak, if I were to write the KEQ like we've learned, which is always products over reactants, I would have that hydronium ion, and my marker's possessed, and I'd have that anion, the A. So I would have the product on the right, and then on the bottom, remember that we wouldn't include water because it's a pure liquid. We would just have HA. So what we do is, because it's just a special case for an acid, instead of calling it KQ, we'll just call it Ka. So if the Ka, if it's a strong acid, you're mostly going to have what, the products are favorites. You'll mostly have the hydronium and the anion. So the Ka is going to be very large. For a strong acid, don't know what's going on here, you guys. And then if it were a weak acid, remember we would mostly have this intact. So this would be large, and that would cause, because it's in the denominator, for us to get a very small Ka. I don't know what's going on. Okay, with my writing. But so let's talk about that. I kind of just did in the previous slide, but if I were to, sometimes we write the K, we show the weak acid as being HW, no different than being HA, just the W kind of makes you think, okay, we're weak, now we have this double arrow. So if I write the Ka expression here, it's really no different than the one in the previous slide. In fact, if you want to use a instead of a W, that's fine. So then, and you can tell that my writing is pretty much illegible. But it would be really similar to that last slide, except for we know equilibrium lies to the left, so we're going to have more intact, so then that would make this a very small number. So there is this handout that you will see in the folder that you can look at. This is a Ka table, and it tells you the values, and so what we see is they're ranked from high to low. These values are so big that they don't even give you a number, because they're going to be, just humongo. So anyways, these are going to be my strong acids. They're going to pretty much 100% dissociate, so the Ka is just limitless. Then we get down and the Kas start to drop. So everything, from here down is a weak acid. Because remember, we're going to have more of what's on the bottom, the intact acid, than the broken up ionized acid. So they keep getting smaller and smaller, so they keep getting weaker and weaker, because you're getting, even a smaller value just means more of it's going to stay intact. So just to summarize, if it's a strong acid, equilibrium lies to the right. We know that we're going to have complete ionization. If I were to draw this, it would be hello? Hello? So I would draw it 100% dissociated in the beaker if I were going to draw it. And the Ka, remember, is going to be very large. And then if you look at the conjugate base, it's going to be A. And that base is going to be very weak, because it's not likely to go back and form HA. And summary of a weak acid, now we have the double arrows. In fact, sometimes we draw it with this other arrow going backwards longer. Again, I'm going to write it in the really generic form. If you want, you could do this way. HW plus water makes hydronium plus W. Sometimes that way you understand more why this is the conjugate base, because then you can see this was the acid, that's the base, this was the base, that's the acid. But I like to write it this way because then when I go into here, I just draw, it has to dissociate a little to be considered an acid, but most of it's going to stay together. So if I were to draw that, that's, how I would show it. If you do it this way, you would just make these hydroniums. So either way is fine. So the conjugate base is that anion W, and it is very strong now because the equilibrium lies to the left, so this is very likely to accept a proton and go back.